Okay, let's get started. This is something I just saw online today. I hadn't seen it before. It's kind of interesting. Self-powered electronic paper. Hang on a second. Well, that's interesting. I'm not getting any audio here at all. Oh, I know why. The audio is going to Zoom. So that's, I mean, basically a piece of paper. Here they've disabled the keyboard and they're using this piece of paper as the input. I don't know about you, I think that looks kind of interesting. So I've got some circuits to look at today. Let's click on download here. And that's a zip file. And let's extract all. And then the one I want to open is flip-flops all. So open that one. Okay, hang on a second here. Okay. So I don't know how big it comes up when you open it. You might have to shrink it down a little bit. I've got several circuits here, but I just want to take them one at a time. This first circuit here, I've got buttons instead of the input pins, the square ones that we usually use. And the way that these work is when you click on them, they send out a 1 as long as you're holding the button down. As soon as you let go of the button, they start sending out a 0. So look at that. Figure out what it does. Feel free to click on the finger and start pushing the buttons and see what happens. So if you click on this once, what happens? Lights this up, right? But here's the cool thing about it. You let go of it, and it goes back to 0, and the LED still stays. And you can keep bouncing on this forever, and once this is lit up, it just stays lit up. And the only way to turn it off, click on this one, okay? And you can click on that one forever, and it'll stay off until you click on S. It'll stay on until you click on R, okay? What this is a memory device. So click on the S. It remembers that the last thing that you clicked on was, if you see a red light there, you know that the last thing that was clicked on was the S button, okay? Now click on the R button. You can let go of the R button. You can bounce on it as many times as you want to. Nothing changes. It remembers that the last thing that was pressed, the last line that had a 1 on it, this one down here. So it remembers either a 1 or a 0. And if you click on the S, it remembers a 1. If you click on the R, it remembers a 0. S stands for set. And when we're talking about zeros and ones, set always refers to putting a 1 in the cell, and clear or reset always refers to putting a 0 in the cell, okay? So this is what's called an SR flip-flop, and S stands for set, and R stands for reset. So set puts a 1 in, reset puts a 0 in. So it's the smallest memory device you can have. It stores either a 0 or a 1. It remembers what the last button was that you clicked on. So it's a storage device, kind of like a light bulb. Okay, turn a light bulb on, it stays on until you turn it off. Yeah, let's wait on the phones until class is over with. Okay, so what makes this different from the other circuits that we've done is that the other circuits depend on what the input is right now to determine what the output is, okay? That's not the case here. This depends on not only what the input is now, but it cycles back again, and it depends on what the input was previously. So this is not a combinational circuit. There's two kinds. Remember those two locks? I've got the pictures of the two locks at the top of today's webpage. There's a combinational lock, and the only way that you can unlock it is you got to rotate and get all the numbers in the right order, and then it will open up. So it's a two-state device. It's either locked or it's unlocked. And whether it is unlocked or not, whether it's locked or unlocked, depends on the state of those 4 numbers that make up the combination, okay? The other one, though, you know, usually you have to put in like 3 numbers on those, so you got to dial right to the first one and left to the second one, then back right again to the third one. And that does not depend on what the current input is. It depends on the current input and some input from the past. So that's not combinational. That's what's called a sequential device, and this is a sequential circuit. It depends not only on what the input is now, but it depends on what the input was in the past. And the reason we can do that is because of this feedback that we've got going on here. So the output of this gets fed back into here, and the output of this gets fed into here. And that might seem kind of weird, but it works. It works. Now, if you look at this down here, the only thing that's different is I just pulled this back, and I changed these from buttons. So up here, they're always going to be 0 until you click on them. Down here, you can set it to 0 or 1, and it'll stay that way. So I changed the inputs from buttons to, they call them pins here. And I added one more output. I took the output from this one and extended it out, and I called it Q complement, Okay, but it's basically the same circuit. And if you click on this one, click on S and make it a 1, and it will stay a 1. And it should turn on Q, okay? The outputs of this are going to be Q and Q complement, and that kind of implies that if this is 1, this should be 0, and if this is 0, this should be 1. So we want that 1 up on top to be the opposite of the one that's on the bottom all the time. So anytime you click on set, this is the output of the circuit, and that's a 1, and its complement will always be available. If you turn that off and click on this, reset the circuit. But let's do this first. Put a 1 in there and a 0 down there for R. And you got the Q lit up? Does that light up Q? Okay. Now set S back to 0. Click on S and make it go back to 0. And Q is still 1, right? Okay. So it doesn't depend on what S is right now. It depends on, what S was previously. Okay, now click on R and make it a 1. And it should reverse things. We should get 0 for Q and 1 for Q complement. Now turn R off, and so now we get 0 and 0 for inputs, and it still remembers that it's supposed to be a 0, right? Okay. So this is about the simplest memory device that you can have. And it's a set reset or an SR flip-flop. And I'm not sure where the name flip-flop comes from. It just kind of, can flip back and forth. I've read several different things about it. I don't think anybody really knows for sure. Now, what happens if you make them both 1? They both go to 0? Okay. We probably don't want that. If one output is labeled Q and the other one's labeled Q complement, we probably don't want them both to be 0 at the same time. So that's kind of a bad input to have. Now let's scroll down a little bit further. And what I'm doing here is, here's my flip-flop. And what I'm doing is I am moving the inputs back a little bit, okay? And what I'm doing is I'm running them through an AND gate. And whenever you see something like this, you're going to see, well, we're only doing this for one more day, I guess, but you're going to see a lot of it in the next day or two. Whenever you see an AND gate, something run through an AND gate, if there's another line here like this, it's a way to turn the AND gate on or off. So if this is 0, I basically shut off both AND gates, and the output is going to be 0, which means the input to my flip-flop is going to be 0, which means the state does not change. Okay? So as long as these are 0, I've basically turned off the inputs, and inputs are going to be 0, 0, and nothing's going to happen. So this is considered an enable, and if I put a 1 on here, notice it goes to both R and S, so they both get enabled at the same time. There's a 1 here and a 0 here, it should turn on this. If I flip it around and there's a 0 here and a 1 here, then I should get a 0 over here. But nothing happens until we turn on that enable. That enable bit is right there, is this symbol. I think this is under wiring. Click on the plus sign next to wiring over there. And is there a clock in there about halfway down? Clock on a computer is just a square wave. It's basically a metronome. So there's a little picture of a very short square wave. It goes down and it goes up, and that's it. So it's one cycle of a square wave. And a clock on a computer is just a metronome that goes tick, 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 tick. And it constantly goes, every tick is a 1, and then it's a 0. And then another 1 and a 0, and a 1 and a 0, and a 1 and a 0. It just keeps doing that forever, okay? And the only time, there's a clock on every computer. We talked about clock speed the other day. We did, didn't we? Clock speed on today's computers is, you know, the upper limit's like around 3 to 4 gigahertz. So a hertz is 1 tick per second. And so 3 or 4 gigahertz would be 3 or 4 billion ticks per second. So what's going on is it's going from 1 to 0 and 1 to 0, 1 to 0, 1 to 0, you know, 3 or 4 billion times every second. And nothing happens on this circuit right here unless the clock is a 1. Okay? And everything on your computer is tied to that clock. Nothing happens on your computer when the clock is on 0. The only thing that happens is, the only time something happens is when the clock goes back up to 1. So what's going on in the computer is this. Clock goes to 1, it enables everything on your computer, and then it goes down to 0. And when it goes down to 0, what's happening? You know, these signals move at the speed of electricity, which is pretty fast, but it still takes a finite time for the electrons to get from here to here, okay? So in between the ticks of the clock, what's happening is it's allowing some time for the signal to propagate through the gates and for the gates to set to their new value. So if it's currently a 0, it needs to change to a 1. It takes a finite amount of time to do that, you know, maybe 1/3 billionth of a second, but that's what happens on the low part, on the 0 part of the tick, okay? So it needs a little time for the signals to pass through. And the reason we've gone from 1 megahertz to 3 or 4 gigahertz, how is it that we can make the clock go faster than it did 40 years ago when they first started coming out with microcomputers? Why didn't they just jack up the clock on those early computers and make them go faster than 1 megahertz? Have any of you ever overclocked a computer? You have? Yeah, that's something gamers like to do to get more horsepower out of their computer. What's the danger with overclocking? Besides overheating? Yeah, and why wouldn't it work? If you make the clock go too fast, the signals don't have time to travel to the next part of the computer. And so the gate doesn't have a chance to get set to what it's supposed to get set to, okay? So you can overclock a computer as, you know, as long as this new clock speed will still allow the signals to propagate through the computer so that everything can go to the next state before the next tick. Otherwise, all bets are off. You don't know what's going to happen. So things only happen when it's a 1. And let's put a 1 on here and a 0 down here. And you can make the clock tick from the keyboard by typing Control-T. So do a Control-T and just do that several times. And watch the clock symbol on the circuit board. The clock symbol goes from a bright green to a dark green. When it's a bright green, it's 1. When it's a dark green, it is 0. So just keep doing Control-T and it'll toggle back and forth between 0 and 1. Now, so you should have Q lit up if you set S to 1 and you set R to 0. And then you hit the clock a few times. As long as that S stays 1, the Q will be set to 1. And if you turn it off, it'll still stay 1. It'll remember that set was the last button or the last input that was a 1. So now put set to 0 and put reset to 1 and do a control T a few times to toggle the clock back and forth between 0 and 1. And it should set our output to 0. And if you turn off the R so that both of our inputs are 0, it should stay where it is. No matter what happens to the clock, it should stay where it is if you got 0, 0 for input. So 0, 0 means no change. A 1 on the S and a 0 on the R means set. A 0 on the S and 1 on the R means reset. Now, set them both to 1. And toggle the clock a few times with a control T. Do you get a red error message at the bottom? And what's it say? Okay, so it doesn't stabilize, and that's something we don't want. We want it to stabilize. So once this happens, I think what you have to do is go to simulate up on the menu and tell it you want to reset the simulation, and it turns everything blue. Then go back to the simulate menu and say simulation enabled. And now you're back so where you can start inputting some stuff again. So 1, 1 for input is not good. We would like to avoid that. We'd like to make it impossible to have 1, 1 for input. So this with these AND gates out on the front is a true SR flip-flop. And once you know that that's what an SR flip-flop is, you know what the inputs are, you know what the outputs are, and you understand that it's basically a 1-bit memory device, you don't have to draw it every time. If you go over to the memory folder on the left side, there should be an SR flip-flop there. And you don't need to grab one and bring it out here. I've put one there for you. Okay, so once you know what this is, if you need one, you can just drag the SR flip-flop out here. It's a 1-bit storage device. S is on the top, R is on the bottom. It's kind of hard to read because it's very small. And we don't need to worry about these down here. These have to do with enabling it, but it's enabled by default. Then we've got a Q for an output. Where's Q on top? Is Q on top? Okay. So Q on top, and it doesn't label the one down here, but that's going to be Q complement. And there's a little triangle there. And if you see a little triangle, the little triangle always means clock. Sometimes it'll say C for clock. Sometimes it'll say like CK or CLK for clock. But sometimes it's just a little black triangle. And so that's where you have to connect the clock. So from this point on, if you want to use an SR flip-flop, just go over to your memory folder over there and grab one. Okay. Now the problem with SR is that if you do have both inputs at 1, then everything kind of blows up. So here's a way to fix it. So we take our SR flip-flop and we change the input bits out here to J and K, and this prevents both inputs from being 1 at the same time. So if I take the inputs to this, let's say this is a 1, and it's currently a 1, so I've got a pair of 1s coming in here, then I've got a 1 coming out here, and it's going to set, okay? And so this will stay set, and this will be the opposite, and I've got this coming back out here, and this is going to be a 0. So there's no way that this can be a 1 when this is a 1. And likewise, if I turn it around and turn this one on, actually go ahead and do that. Just get your finger up there and click on the K and make it a 1. Actually, this is tied to a clock as well. So nothing's going to happen until you toggle the clock. But toggle the clock. J is to set. K is to reset. And you should be able to turn on J, toggle the clock a few times, and it should go to 1. You should be able to turn on K and turn J off and toggle the clock a few times, and you should get 0 for an output. You're not getting 0 for an output? Are you or not? Are you not? You are? Are you getting 0 for an output? Oh, that's right. It's reversed on this one. I'm sorry. I was still doing Q on the bottom. Q's on the top on this one. Okay, so it's working, right? What happens if they're both 0? And you hit the clock a few times. Control T. Nothing happens, right? And what if they're both 1? And you toggle the clock a few times? Switches back and forth. But it doesn't give you that oscillating feedback, okay? It does stabilize. So we basically eliminated that. So the only difference between this and this is that you can't ever get into a bad state when you're doing this one like you can with this one. So it's okay to have both inputs be 1 here. You just know that when you do, it's going to toggle back and forth between 1 and 0 on every tick of the clock. Okay. Scroll down to the next one. And the next one is, which one am I on now? Am I on this one down here? Yeah, I'm on this one down here. Okay, so it's second to last one on there. This is exactly the same as the one up here, except I've got a constant for input. And I'm always going to zap this with a pair of 1s every time. And so try this one and toggle the clock a few times. And because I've got both 1s there, for inputs, it's basically going to do the toggle thing. That's all that this does, is it toggles back and forth between 0 and 1. Okay. This is called a toggle flip-flop. If you go over and look at your memory devices over here, I forgot this one. There's a JK flip-flop in there that you can use. There is a toggle flip-flop in there that you can use. The toggle flip-flop, so there's the clock, there's a little triangle, and T is for toggle is the input. There's only 1 input, and every time you zap it with a 1, it's going to flip back and forth between a 0 and a 1. Okay? And so once you know how that works, you can just use a toggle flip-flop from the toolbox over here. And the last one, this looks just like this one up here, except I've got an inverter. So try that one out. See what that one does. What happens if you got a 1 for input? And you zap the clock a few times. Get a 1 for output, right? What happens if you get a 0 for input and you zap the clock a few times? So all it's doing is it is storing what is here, right? And that is called a data flip-flop or a D flip-flop. So you put the data that you want to go in right on this line right here, and whatever is there, whether it's a 0 or a 1, when you zap the clock, it gets loaded into the flip-flop. Okay, so we got several variations, 4 different versions of a memory device. But a flip-flop is just a 1-bit storage device, and you can use whichever one is appropriate for whatever problem it is that you're trying to solve. Okay, let's go back to the files that we downloaded. It's in a folder called memory. And double click on register 4-bit. And let's take a look at what we've got here. I've got 4. So a register is a storage place in the CPU, and it stores data. And on today's computers, those registers are like 64 bits wide or 128 bits wide, but the principle would be exactly the same as what I've got here. We just make this stack a whole lot taller. So if you want to put something into a register, you have to put the data on some input lines here. That's what input 0 through input 3 is. And then we've got our output here. And nothing gets loaded in until you zap the clock. So you can click on it or just do a Control-T to go back and forth between 0 and 1. I've got all zeros for input, so what gets loaded into the registers on every tick of the clock is going to be a bunch of zeros. Now let's change this to a 1 and tick the clock. And after one tick of the clock, it propagates through the flip-flop, and now I've got a 1 here for output. So my register now holds the number 0001. If I decide I want to store the number 5 in there, I turn on this one and I zap the clock. 2 more ticks of the clock, actually 1 full tick of the clock, but two clicks of the mouse. And now I've got the number 5, okay? So I had to connect all of my inputs up to one of the D inputs here. We don't need to worry about the ones on the bottom at all. We got to make sure we got a clock connected here so we can make sure that things only happen when we want them to happen. And then we've got our outputs here. There is a Q complement down here, which we are rarely going to need. So we'll just leave that. So that's a 4-bit storage device, 4-bit register. Okay, let's go back over here and let's go to memory and let's do register 8-bit. And I'm probably gonna have to shrink this down a little bit. Let me see. Yeah, so actually I did 2 versions of it. This one over here is just an extension of the one I had before. The one over here on the right, though, I'm going to zoom in on that a little bit. Yeah, it's too far. Okay. And then I'm going to try to scroll over here and look. And so what I did was, instead of having 8 individual 0s and 1s over here, I made an 8-bit input. And I ran that through a splitter and then ran all the 0s and 1s to the D inputs on here. I've got everything connected to a clock again. And then when I get my outputs, these are the low order bits right here. So I tie them into the splitter and they go to the right side, the 1s column. And these are the high order 4 bits, and I run them through a splitter and I tie it into this hex display, and that's the 16s column. So whatever number I put in here, if I change this to a 1, and I better toggle the clock though, I get a 1 for output. If I change that to 101 and toggle the clock a few times, I should get the number 5 for an output. And the biggest number I can put in here is all 1s, which would be a pair of Fs. So that's all pretty straightforward. I mean, once you understand how one flip-flop works, it's a piece of cake to start making registers made up of multiple flip-flops. Okay, let's go back to our memory folder, and there's a counter there with T flip-flops. Double-click on that, and that one is kind of an interesting circuit. Let's take a look at what it does here. Okay, well, I've got a clock down here that's attached. These are toggle flip-flops, by the way. Every time I zap one of them, it's going to toggle back and forth between 0 and 1. Now, so this is a 4-bit counter. It'll go up to 16. I don't know if I want to write all 16 numbers on the board, but let's do some of them. 0001, 0010, 0011, 0100, 0101, 0110, 0111, 1, 0, 0, 0, 1, 0, 0, 1. I guess I'll do them all. 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and then at the very bottom, 4 ones. Okay? Now, I want you to look at this first column here. What do you notice? It toggles back and forth between 1 and 0. 1, 0, 1, 0, 1, 0, 1, 0, all the way down. Okay? Look at that column. Every 2. Okay? And I should have started with 0, shouldn't I? Okay. So 2 here, 2 here, 2 here, 2 here. This one, every 4. This one, every 8. If I did one more column, every 16, it's going to change. Okay? So this changes when there is a 0 and a 1 here before it. So this one's just going to toggle back and forth, back and forth, back and forth, back and forth. Okay, and then I got to decide, you know, when do I toggle this? Okay, and I toggle this when, looks like when the last bit over here was a 1. Okay, and when do I toggle this? Take a look at this. This is where it changes, and this is where it changes. And what do you know about the previous number? It had a pair of 1s. And we only got 1 here in this column. This is where it changes. And when does that change? When there were 3 1s on the previous one. Okay? So this toggles on every tick of the clock. This toggles on every other tick of the clock. This toggles on every 4th tick of the clock. And you can tell by looking when it toggles, you know, look at that number on the previous tick in the next lowest column. So that's how it works. And so what you can do is you can actually build a counter. So this number right here, let's make this a 1. Otherwise, nothing's going to happen at all. So make that a 1 and zap your clock once. Okay? And this became a 1, got loaded into the register, and then the output was connected to this, so we get a 1. Now, let's tick the clock again. You got to do 2 clicks. Now, I've got a 0 here, and okay. Now let's toggle it once more, and I'm getting a 1. Let me see. I've got a 1 here, I've got a 1 here, and I'm going to get a 1 here on the next tick of the clock. And let's go ahead and tick the clock. You get a 1 here, and these go back to 0. So this says if I've got a 1 on the previous tick, it takes you know, half of a tick to propagate from here to here. But if I got a 1 on the previous tick, then on the next tick, I'll have a 1 coming out of here. And if I had a 1 on the previous tick for this one, then I'll have a 1 coming out of here. And we can count every time you do 2 ticks of the clock. So I'm on 6 and I want to go to 7. I'm sorry, that's not 6, is it? That's a B. Okay. So I'm back to 0 now. If I zap it, I get a 1. And on the next tick of the clock, there's going to be a 1 and a 1 coming in here, so it's going to zap this one. And I'm going to toggle this one so it goes back to 0. This is going to go to 1 again on the next one. I got a pair of 1s. And now this is going to toggle back to 0. This is going to toggle back to 0. And the 1 coming out of here is going to propagate through here. And I'm going to get a 1 in that one. And I get the number 4. So we just build ourselves a counter. And it's not very hard to do. Okay, now let's go back to our home page. And let's take a look. Actually, let's click on memory notes here. Oh, crap. It's not there. Then let's go back over here to our memory folder and open up the 4x3 memory. What I was going to look for in the notes is there's a picture, and it's in the book as well, I think. There's a picture of a memory chip on there. You can go out and you can buy a memory chip, you know, a little black plastic package about this long and about this wide with pins on it. And you can buy one like here's a bit, and here's an input to it, there's an output bit, and there's an input and there's an output. What we've got is a D flip-flop, 4 of them up here, we got 4 of them down here, and 2 pins on each one, so 8 for input and 8 for output. Okay, so I've got a 1-byte memory chip is what it is. Okay. Now, today's computers have billions of bytes of memory on them. So if this was the way that I implemented memory on today's computers, I would have to have a circuit board big enough to hold billions of these chips, which would be a really, really big circuit board. Okay. So that's not how you do it. If an engineer is designing a simple circuit and all they need is to store 1 byte, then they can use this. But if you want to do it on a computer and you need to have lots and lots of bytes of memory, you need to have a way. Actually, if I wanted this to have 1,000 bytes of memory in it implemented this way, I would have to have 2,000 pins. 1,000 input pins, 1 for each flip-flop, and 1,000. So that's kind of a big chip. 500 pins on each side. So obviously, that's not how memory is implemented on a computer. So how is it implemented on a computer? Let's take a look at this. Wrong arrow. Okay. So let's take a look at that. And it looks kind of ugly. I'm probably sharing the wrong screen now. I want to share. No, not that one. This one. Okay. It looks kind of ugly, but it's actually pretty easy to figure out. So this is, let's start at the top. A word of memory is a bunch of related bits. You know, the word size on today's computers is usually like 64 bits. You ever gone to download a program and ask you if you want the 64-bit or the 32-bit version of Windows? So those registers, those storage locations in the CPU are probably 64 bits. And each one of them has an address. Well, so this is the word size of this memory is 1, 2, 3 bits. It's 3 bits wide. And I've got 4 memory cells. This is my first memory cell. This is my second memory cell. This is my third memory cell. This is my 4th memory cell, okay? Those are just D flip-flops. I've got a clock here and something called write enable. And you can figure out what that means. That I'm only going to write something to this memory if this is turned on and the clock goes to 1. Otherwise, nothing gets written. Now, we've got 3 inputs over here. And this little device down here, everything below this line, these 4 AND gates, that should look familiar to you. What is that? It's one of those 4 that we looked at, was it yesterday? Decoder, encoder, multiplexer, or demultiplexer. Which one is it? And it routes it. So it's not one of those 2. So it's either a decoder or it's an encoder. What'd you say? Encoder. Encoder? Yeah. Flip the coin again. What's a decoder do? It takes a binary number. So say you've got 3 bits. And it tells you what that number is by lighting up one of 8 different outputs. Okay? So it's decoding, that's what they call a decoder. It's taking a binary number and it's decoding it for you. Okay? This is taking a binary number, a 2-bit binary number, and if the number is 0, this line is going to light up. If the number, this line is going to light up. If the number is 2, this is going to light up. If the number is 3, this line is going to light up. Okay? Go down to the bottom, turn on your hand up there, and if you got 0, 0 down there is what the default should be. Change it to a 1, 0, 1. This line should light up. Change it to a 1, 0. This line should light up. Change it to a 1, 1, and that line over there should light up. Okay? When you're looking at this stuff, what you need to remember is that if this line is lit up and these are not lit up, then what we're probably doing is we're turning off anything happening in these 3 columns over here. The only place where something's probably going to happen is where we've got a 1 right here. So we're selecting, these are labeled S. They could also be labeled A. S for select, but A for address. So the address of this 3-bit memory word right here is 0, 0. The address of this is 0, 1. The address of this is 1, 0. And the address of this is 1, 1. So we're specifying an address that we want to either read memory from or write memory to. Okay? Okay, now let's turn on the write enable. And right now we've got zeros out here. Let's put a 1 and a 0 and a 1 out here. Okay. Now you see what's happened? This 1 here is made available to this flip-flop and this one and this one and this one. But because my address down here is 0, 0, if your address isn't 0, 0, move it back to 0, 0. This is the only vertical line that's lit up. Okay. And this vertical line also goes over here. And I'm sorry. Now let's do our clock. Get your clock to 1, okay? And now, write enable means that on the next tick of the clock, when the clock goes to 1, we're going to take whatever our input is, and we're going to write it into the memory cells for word number 0 because 0, 0 is what I specified down here. So there's a 1 here, it zaps this, and now I've got a 1 stored there. There's a 0 there, so I've got a 0 stored here. And there is a 0 here, or 1 here, so I've got a 1 stored up here. So I'm making that available to the D input, and the little triangle up there is the clock. And remember, nothing happens on these unless you zap the clock. Okay. Now let's change our address down here. Let's tick the clock so it goes off. Let's change this to a 0, 1 down here for our address at the bottom. And that should be word number 1, which is these 3 bits right here. And let's put the number 7 in word number 1. So put all of our inputs here to 1. These are still all 0s in word number 1 because I haven't zapped the clock yet. Zap the clock, and all 1s get read into that memory cell. Okay? Now take a look at your outputs. I've got output 0, which is going to output one of these bits here. I've got output 1, which is going to get one of these, and I've got output 2, which is going to output one of these. And what determines what gets output is which one of these vertical lines here, one from our select bits, which one of these vertical lines is turned on. So this is the one that's turned on, and so it is enabling the output from this. And what's the output from word 0 and word 2 and word 3? 0. So basically, the only output of this is going to be whatever comes in on this line right here. Same thing down here. This is coming from the second bit in word 1, and this is coming from the third bit in word 1. And so my output here is exactly the same as what's stored in word 1. Okay? Let's set our clock back to 0. Let's change our input down here to 1, 1. We're skipping over word number 2. And let's try, let's put the number 6 in there. So our input would be 0 on the top and then a pair of 1s. Okay? So I should get, because my address is specifying the number 3, it should take me to word number 3 here. And it is enabling the output so I can get what is in word number 3 here. Right now, it's just all 0s. But when I zap the clock again, 2 things should happen. A 1 and a 1 and a 0 should get loaded into here, and that should also appear on my output because that's what I've got activating my output lines here. So go ahead and zap the clock once, and I get 0, 1, 1 here, and I get a 0, 1, 1 here, showing me that if I go to this address, this is the data that is stored there. Okay? So that's kind of a quick explanation of what's going on there. And what you should do is you should make sure that you understand everything about how this works. Okay. And it's not really that hard because all the rows are the same, all the columns are the same. And this is just a decoder down here. And, you know, the inputs and the outputs are pretty straightforward. So here's a couple of questions for you. This is, each word is 3 bits tall. And I've got 4 of them. How would this change? How would this picture change if I had 3 bits down here instead? I will find out for sure on the test if you understand how this diagram works. If I have 3 select lines instead of 2, how does that change things? Obviously, you're going to have to add some stuff. Yeah.
Does that change how much you'd be able to store in it?
It would change how many words you can address, yeah. So how many words can you address with 3 bits?
What's that?
From 0 to 7. So 8 actually, yeah, 2 to the 3rd. So if I had 2 more bits here, that means I've got a 3-bit, I'm sorry, if I had 1 more bit here, that means I've got a 3-bit number. So I want to select anything from 0 up to 7. Right now I'm selecting one of 4 things. So I would have a decoder here that had 3 inputs, but 8 outputs. If I had 4 inputs down here, that means I'm trying to address something from 0 to 15. So I would have 16 words, okay? More columns here. If I had 5 inputs down there to select an address, basically this is an address. If I had 5 things down there, 2 to the 5th is 32. So I would have 32 columns now. And my decoder down here would have 32 lines coming out, but only 5 lines coming in. And so on. Now, on today's computers, we don't have bytes that have 3 bits per word. On today's computers, we have bytes that have 8 bits per word. So if I wanted to make each memory cell store a byte, then I would have to make this 5 more instead of 3. I'd have to have it made 8 bits tall instead of just 3 bits tall. Okay? So if I had a 32-bit number down here, it would have 2 to the 32nd lines coming out, which is 4 billion. And if I had 8 rows of data here, I would have 4 billion bytes of data that I could access. Okay. Now, if you think about that, it's going to be 8 bits tall, and it's going to be 32 billion bytes wide. So it's going to be a very long, very skinny integrated circuit. And obviously, that's not how it's done. If you've seen integrated circuit chips, what shape are they basically all the time? Actually, they're almost always square. They're pretty close to being square. So in order to do this, instead of having 32 bits at the bottom, what I would have is I would have 16 bits here, and so I got 16 lines coming in, and I would have 2 to the 16th lines coming out, okay, which is 64,000, 64K. And then I would have another decoder down here, and it would also be 16 bits wide, and I would have 2 to the 16th lines coming out here. So every place where I've got an intersection here, there would be one bit of memory there, okay? And so I've got 2 to the 16th going this way. I've got 2 to the 16th going this way. What's the area? It's 2 to the 32nd. So there would be, on this square chip, there would be 2 to the 32nd bits of memory. And the high order 16 bits would be plugged in here. The low order 16 bits would be plugged in here. This would light up exactly 1 line in this direction. This would light up exactly 1 line in this direction. And at the intersection of those 2 lines would be the data that's specified by this 32-bit address. So now how many pins do you need to specify an address on this chip? You need 32 pins to specify an address. 16 pins here, 16 pins. It's a 1-bit memory, just like, actually it's not like this. This is a 3-bit memory. It's a 1-bit memory, so at the intersection of every one of those, we got 1 bit. So how many data input lines do you need? You need 1 in, you need 1 out. So now we're up to 34 pins on a chip. You need one for power, you need one for ground. You probably need a read pin like we here, or a write pin, and I don't know, maybe a few others. But so we're probably talking, somewhere around 40 pins on a chip if you design the memory this way, okay, as opposed to this way over here. So how can you do that? Well, we can design chips that have components on them, flip-flops on them. Actually, technically, it's not a flip-flop on computer memory, but you can think of it as being a flip-flop. So we can design circuits that are very, very, very small. And this is reasonable. You can actually do this, okay? Now, what do you suppose the next step would be? So they figure out a way to make the chips a little bit smaller. What's the next step going to be after this? Well, the next step would be one more line here for input, right? And if you can squeeze twice as many, so that's going to be twice as many. 2 to the 17th is twice as much as 2 to the 16th. So we're getting twice as much stored, squeezed in the same amount of space. That's Moore's law. And up here, 17. And so we double it in both directions, and we got 4 times the memory on that chip that we had before. And if you look at the history of memory chips, they'll go from like 1 billion, let's back off to millions, 1 million bits, and the next one's not 2 million bits, the next one's 4 million bits, because they doubled it in both dimensions. And then the next one after that would be 16 million, because they double it in both directions. So you multiply by 4 instead of by 2. So this is how a memory chip would really be designed, except for a whole lot more. But you specify an address down here, the address gets run through a decoder, or if you want to do it in 2 dimensions like that, and just have 1 bit at the intersection. By the way, if we did it this way, we would need 8 of these chips to make up a byte. You'd have 1 bit on this chip, 1 bit on this chip, 1 bit on this chip, and they'd all be at the same address on different chips. So that's how it works. Make sure you understand how to do this. Okay, let's take a break. Start up again about 20 till. Yeah. We'll do it after class. Okay, I wanted to take a little bit of time to, we're going to have a test on chapter 3, not tomorrow, but when we come back on Tuesday. Okay. And a few days ago that we were having Labor Day, but apparently we're not. Yeah, so drop in fall break and Labor Day, and that's what I thought we were doing too. But so class on Monday. When you come back on Tuesday, test chapter 3 class, and we can spend some time on it tomorrow. Well, and there. The labs, because today's assignments weren't until 9 o'clock, I didn't want to start grading some of them yesterday and finish them up today. I like to grade them all at the same time. And so I didn't get your stuff graded for today, but I'll have everything for you tomorrow. So lab number 2, if you want to pull that up, if you want to go to our homepage and pull it up, we want to build a parity generator for a 3-bit word. And we want a 1. Function is going to give us a 1 wherever the number of ones in the input is odd. Okay, so our input could be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, or 1, 1, 1. And I want a 1 whenever we've got an odd number of 1s. So there's 1, 1 here, there's 1, 1 here, there's 1, 1 here, and there's 3 1s down here. So my function is going to look like that, okay? And so we care about where the function is 1. We don't care about where the function is 0. This is the row where A is 0, B is 0, and C is 1. So A has to be complemented before I run it into the AND gate. B does as well, C does not. Down here, A is 0 and C is 0. So A has to be complemented and C has to be complemented before I run it into the gate, and B does not. Down here, A is 1 and the other two are 0. So A, B complement, C complement. And down here, they're all 1, so it's A, B, C. So the sum of products, this is a product, this is a product, this is a product, this is a product. So the sum of products is going to be A complement, B complement C, or A complement, B, C complement, or A, B, or A, B, C. And I did not ask you to try to simplify that. I don't know if it can be simplified or not. I kind of think it might not be able to simplify it. So you had to create the circuit. This is going to run into an AND gate. If I've got A and B and C over here, I'm going to need 4 AND gates, and A needs to be complemented, B needs to be complemented, whoops, and C does not. A needs to be complemented, B does not, C does. Down here, A is not complemented, but B and C are. And then down here, and I run all of them through one big OR gate. And that's what you should have ended up with. So the next one, we wanted to create the same circuit, but we want to do it with only NAND gates, okay? The reason for using NAND gates is because NAND gates actually take up less space on the board. It's easy. You know, we went through the proof in class. I'm not going to ask you to prove it. All you have to do is remember what the outcome of the proof is. The outcome of the proof is you change these to NANDs, and you change this to a NAND as well. That's all you got to do. Okay. Then the next part of lab number 3 said, create a product of sums. And we proved this one, but you don't need to, I'm not going to ask you to prove anything on the test. What you do have to remember is how to get the answer. So you look at the rows where the function is 0. You complement everything and put a plus sign in between. So this row is going to be A or B or C. I got to complement the zeros. Down here, I complement everything, so it's going to be A, B complement, C complement. ANDed with A complement or B or C complement. ANDed with A complement or B complement or C. Okay. And then the circuit for this, A, B, C. I'm running everything through an OR gate. And it's A, B, C. Nothing has to be inverted. Invert the B and the C. Invert the A and the C. And invert the B and the C on the last one. Run them all through an AND gate. And that's what you get. and then convert that to NORs. And again, all you gotta do is remember the results of the proof. You change these to NORs by putting a little bubble on the end. You don't have to change anything else. And then this becomes a NOR as well. So just change everything to a NOR, and you're good to go. Yeah.
Last one, don't we invert the A and C, or A and B, not A and C?
You're right. I'll do stuff like that on purpose every once in a while just to make sure you're paying attention. But accidentally, and then you better be paying attention. Okay, number 4. We did the first Carnot map. The second Carnot map, I'm not going to do everything. Let's go back here. We were doing the low order bit, and our Carnot map, we did the high order bit together yesterday, so we don't need to redo that today. So up here, over here, I've got AB, 0, 0, 0, 1, 1, 1, 1, 0. Up here, I've got CD, 0, 0, 0, 1, 1, 1, 1, 0. And there are only 4 places where you got a 1. You got a 1 in the ones column if you divide it by 3, 4, or 5, or 9. So 3 is here. 4 is here, 0, 1, 0, 0. 5 is here, and 9 is 1, 0, 0, 1. And if it's 0 or 1 or 2, or if it's 7 or 6, we get a 0. And down here, if it's an 8, we get a 0. And these others are the hex digits, A through F, 10 through 15. And we don't care because we're making the assumption that we will never have inputs of 10 through 15. So we don't care. Now, what you want to look for to do the most factoring, you want to look for the biggest rectangle, then go for it. Okay? So you want the biggest possible rectangle, and you can't have a rectangle with a side of length 3 because that doesn't correspond to any factoring that we can do. So you look for the biggest possible rectangle you can find that includes all of your 1s. Okay? Well, here is the biggest rectangle that gets those 2 1s. This rectangle down here, that's the biggest rectangle I can get. That one, which also includes x's. And then this one is left over. But the top is connected to the bottom, and the side is connected to the side. Actually connected to this down there, and I can't get a 2 by 1 rectangle for that one. Okay? So now I got to go back and figure out, what is all this stuff? Well, this is the intersection of these 2 rows and these 2 columns. These 2 rows are the rows where B is 1. So B is part of my term, and these are the 2 columns where C is 0. So B, C complement takes care of those 2 1s right there. Down here, it's the intersection of these 2 rows with these 2 columns, okay? These 2 rows are the rows where A is 1, right there and right there. And these 2 columns are the columns where D is 1. And then this is the column where C and D are 1, intersecting with the 2 rows, this row and this row, where B is 0. So it'd be B complement. If we want to do these in alphabetical order, then we write it like that. Okay. So that's what you should have come up with. Did you remember that this is connected to this? Did you remember you can have them overlap, so you can do two of these here and use the X twice? Okay. So you end up building two circuits there, one for the high order bit, one for the low order bit. You'll get a number from 0 through 3. Divide 9 by 3, you get 3 for an answer. And you treat it as a 2-bit number representing your answer. If you want to get fancy, you could connect them. Okay. And the last lab that was due today is this problem. And the function is A complement B complement C complement, or A complement B C complement, or A complement B C, or A C. Okay? This corresponds to the number 0, 0, 0. This corresponds to the number 0, 1, 0. This corresponds to 0, 1, 1. This corresponds to 1, 1, 1. Okay? So this is going to be line 0. This is going to be line 2. This is going to be line 3. This is going to be line 7. And we want to have a multiplexer, and the multiplexer block diagram looks like this. That's line 0, and that's line 7. And I want, my input is going to come from down here. It's going to be a 3-bit number. And there's only one output. A multiplexer is a switch. It grabs one of these and passes it on to the output. And so if I want this one to be connected, I put 0, 0, 0 here. Well, if I put 0, 0, 0 here, it's going to connect this one. What do I want? I want a 1 on that line. And if I put a 2 here, 0, 1, 0, I want a 1 to be passed on. This is line 2, so I need to put a 1 here. And if there's a 3 down here, I want a 1 to be passed on. So on line 3, I need to put a 1. And on line 7, I want a 1 to be passed on, so I need to put a 1 there. So what I need to do is just put a constant 1 over here, put a constant 0 over here. And this should be connected to 1. This should be connected to 1. This should be connected to 1. And this should be connected to 1. Line 0, line 2, line 3, and line 7. Well, the other times I want a 0 to be passed on. So I want all of these other lines to be connected to line 0. Okay. So that's what you should have had. And then the last one, I didn't tell you how to do it, but you know there's only one output from a digital function. So you got to take those 8 outputs and somehow get one output out of them. And the diagram for this one, for a decoder, looks like this. 0 through 7. And a decoder is going to take a 3-bit number, a binary number, and it's going to decode it. If it's 0, this line's going to light up. If it's 1, this line's going to light up. So it's basically telling me what the binary number is, hence the name decoder. Okay. Now, if I put 0, 0, 0 here, this line is going to light up. And when that line lights up, I want an output of 1. So I'm going to run that through an OR gate. When I put 0, 1, 0 here, that's line 2, and I want a 1 to be output, so I better connect that. And if we got 0, 1, 1, I think that's the next one, yeah. Then I want this line to light up. And if it lights up and I run through an OR gate, I'll get a 1 for output. And if I put 1, 1, 1 down here, that'll light up this line, and I want a 1 to be output. So that's what you need to do. If the number is 1 or 4 or 5 or 6, just leave them. Don't go anywhere. Okay. And that is what we were looking for lab number 5. Okay, let's actually, I had a bad link out there for the notes. Is that one a bad link too? That one's not a bad link. Okay, so let's go ahead and open that. Okay. Right there. Okay, so the next step in our looking at how a computer works is we're actually going to look at, it's not a real computer, it's a simulated computer, it's a fake computer. The only place this computer exists is in the mind of the author of our book, and it exists in the software simulator that she created to simulate the computer. And she calls her computer Marie. Marie is an acronym. She must have sweated over this one for a while to come up with it, but it is, I forgot what it is. Got in here somewhere. It's down here a ways. Okay. Machine architecture that is really intuitive and easy. Okay. Okay, so we're going to look at this fake computer, this fake central processing unit. It's fake, but it behaves the same way as real computers do, as real CPUs do. The difference is this is a really stripped down version, and because it's a stripped down version, okay. Because it's a stripped down version, you know, we can actually understand how it works. If we were to take one of today's real computers and try to look at it and figure out how it works, it would take a whole lot longer than 1 semester. So the components of our computer, this computer has a central processing unit. You know, a regular computer has an input device like a keyboard and a mouse. It has an output device like a monitor and a printer, and it has a CPU and main memory, and it also has some kind of secondary memory like a hard drive or, optical drive or USB drive or something like that. We are looking at two parts of a computer. We're looking at the CPU and we're looking at the memory, and that's it. And a little bit of history here. One of the very first microcomputers, the first one I ever had, was the Apple II. It used something called a 6502. I have no idea where that number comes from. It had an 8-bit CPU. You could read 8 bits from memory at one time. You could process 8 bits, and then you could send them back out to memory. And even though you could only manipulate 8 bits at a time, you could do some amazing stuff on an Apple II computer. The IBM PC, which was a few years later, used something called an 8086, and the next generation was the 286, the 386, the 486, and they didn't call the next one the 586, they called it the Pentium instead. And the reason why they did that is because they found out that you couldn't trademark a number, but you could trademark a word. So they quit using numbers because other companies were making compatible chips, and they were saying, well, we just built an 8386 CPU, and Intel couldn't get them not to call it an 8386 because they couldn't trademark a number. So after the 486, they started using words instead so they can trademark the words. So I should probably have a little TM next to that and next to that. But this was kind of a hybrid between an 8 and a 16-bit computer. We'll talk a little more about it one day before the term ends. And this was a 16-bit computer. This was a 32-bit computer. And now up here, we're into like 64-bit computers. The Macintosh originally used a 16-bit processor. They skipped all that 8-bit stuff. And then they started using something called PowerPC. This was from Motorola. And I don't think Motorola does much in the way of making chips anymore. So they kind of started falling behind. And they got what's called a PowerPC processor from IBM, and they used that for a while. And then around the year 2000 or shortly after, they started using Intel's processors, which is why if you have a Macintosh now, you can run Windows on it because it runs the same processor that Windows computers run. But they are planning to move to their own chips sometime soon. I don't know what the exact date is, but they're going to start making their own. Actually, I don't think they make them themselves, but they design them, and I think they have some chip company build them for them. Okay. So the CPU has two parts. It's got something called an arithmetic logic unit, which is almost always just referred to as the ALU. And that's where you can do, guess what? You can do arithmetic and logic. So you can do addition, subtraction, multiplication, division, and you can do ands and ors and nots and stuff like that. And then there's a control unit, which basically feeds stuff to the ALU and decides which instruction is going to get executed next and so on. Okay. Any CPU has a number of memory locations for storing data, and those are called registers. We looked at a 4-bit register and an 8-bit register a few minutes ago. So a register is just a storage location that is on the CPU. Some of those are special purpose registers. You can only use them for one thing. Others are general purpose registers. If it's a general purpose register, that means you as a programmer can do whatever you want to with it. You can put any value in there that you need. And then the other thing we've got is we've got main memory. And that holds the data, and it holds the instructions that make up the program and the data that goes with the program. So we got some special purpose registers. There is something called a program counter register, and this is, you can tell from the word counter what it does. It counts. And it starts off with the value of the first instruction in it, and then it adds 1, and that's where the next instruction is. And then it adds 1, that's the address of the next instruction, and so on. So the program counter always tells you where the next instruction is. the instruction register holds the instruction that's currently being executed. This is the way a computer program basically works. You have instructions and you have data, and they're stored in main memory. So here's our CPU, and here is our main memory, which is just a big stack of bytes. Here's byte number 0, and here's, the last byte. And so let's say your program gets loaded into this area of memory right here. Memory is addressable. That's what that decoder was in our little 4x3 picture a little minute ago. That's the address. And to access a memory cell out here, we've got lines going to every single one of these, okay? And if I want to access this memory location at the beginning of your program, I have to light that line up. So the way I light that line up is I've got something over here called a memory address register. And the memory address register holds the memory address, and it's got all these lines coming out from it because it's basically just a big decoder, and it lights up the line that corresponds to the address that you put in there. And that means that this is the only active cell in main memory, and you can write to it or you can read from it into the CPU. And this is actually part of the CPU. I probably should have drawn it a little further over here. There is a program counter register, and what the program counter does, it starts off with this address in it. We fetch that instruction, then we add 1 to it, so it's ready to go here and get the next instruction. We add 1, and it's ready to go there and get the next instruction, and then we add 1 to it. We just keep on doing that as we work our way through the program. Okay, the way programs get executed is from top to bottom. You start with the first instruction, then you go to the next one, you go to the next one, you go to the next one. It's like reading a book, okay? So the program counter always points to the next instruction. If we are reading an instruction in from here, that's the first instruction in our program, we have to get into the CPU. And there is a memory, sometimes it's called a memory data register, sometimes it's called a memory buffer register, it depends on which book you're reading. And this is, a buffer is in a computer, a buffer is like a temporary storage location when you're moving from one place to another. So this is a buffer between memory and the CPU. And when we say go fetch an instruction, that instruction gets loaded into the memory data register. And from there, it gets copied into something called the instruction register, which we're going to abbreviate IR. So here's the instruction that is going to get executed next. Okay. So we're constantly doing this fetch execute cycle. We get an instruction, we increment the program counter, we put the address in here that's in the program counter, we go out and get that instruction, we copy that, it comes into the memory buffer register, it gets copied into the instruction register, and once it's in the instruction register, then the CPU can execute the instruction. We'll talk about how it does that in the very near future. So we've got a program counter here, and it is always pointing at the next instruction. So we finish the instruction, then we go look at the program counter, and it's pointing now down here, and we say, okay, now let's go get that one. We bring it in, copy it in the instruction register, and then we execute it. And that just keeps on happening over and over and over again at the rate of, on today's computers, at the rate of billions of times every second. Okay, so that takes care of these first 4 here. There's also something called a status register. And what it does is it typically holds some single bit values called flags. And a flag is just another word for a Boolean. So if it's a single bit, it's either 0 or 1. As we've been doing, 1 is always the value true, and 0 always represents the value false. Okay. We've got an AND bit in there to tell us if the answer of the last operation was negative. We've got a carry bit in there that tells us if there was a carry when we did the last instruction. We've got a Z bit that tells us if the result of the last instruction was 0. And we've got a V for overflow. They didn't do O because I think you would be confused with the number 0. And if there was an overflow, we get a 1 in there. 1 is always representing true, and 0 is always representing false. So what can you do with a register? You can clear it, which means set all the bits to 0, or clear all the bits to 0 might be a better way to do it, because set usually means put a 1 in there. You can load something into a register. You can do arithmetic on it. You can do logical operations on it. Every computer has something called a bus. And a bus on a computer is just like a bus in real life. In real life, a bus hauls people back and forth from one place to another. On a computer, a bus hauls data back and forth from one place to another. So there's a bus connecting the CPU to main memory. There's a bus connecting the CPU to any peripherals that it needs to be connected to as well. Okay. There's a clock in there, which we talked about a little bit earlier. A clock doesn't actually keep time. It just goes tick, 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 billions of times every second. Okay. Memory, we talked about this a little bit ago. Memory addresses are run through a decoder. So if I have a 2-bit address, I can access 4 memory cells. If I have a 3-bit address, I can access 2 to the 3rd memory cells. If I have a 32-bit address, I can access 2 to the 32nd different memory cells. That address just gets run through a decoder. So a little bit of history here. The Apple II computer had 16-bit addresses. So what's that tell you? It could access 2 to the 16th memory cells, which is 64K. 2 to the 6th times 2 to the 10th. 2 to the 10th is 1K, 2 to the 6th is 64. So it could access 64K of memory, which is nothing today. The IBM PC, the original version of the IBM PC, had a memory address register that was 20 bits wide. So it could address 2 to the 20th, which is 2 to the 10th times 2 to the 10th, which is 1,000 times 1,000, which is 1,000,000. So it could access a megabyte. Those extra 4 bits made a lot of difference. And later versions of the IBM PC have 24-bit, 32-bit, and 36-bit addresses. 2 to the 36th is 64 gigabytes. That's a lot of memory. And there are probably processors that have more addressable memory than that. But if you're looking at microcomputers that you and I might buy, I'm kind of thinking 16 gigabits is probably near the upper bound on computers that people would buy today. Okay, I've talked about this. Most of computers today are byte addressable, which means you can access an individual byte. Okay. So here's a picture of what Marie looks like. This is the CPU, this is the memory. Memory is just a stack of bytes is all. Each one has an address. And it has 4,096 bytes of memory, which means its memory addresses are 2 to the 12th. 12 bits wide, gives you 4,096. So we've got an arithmetic logic unit with a register in it called an accumulator. We've got a way of getting data out of it. We've got a way of getting data into it. We've got an output register, an input register. The memory address register connects to main memory. The memory buffer register, I don't know why they don't have an arrow here connecting this, because that is also connected to main memory. And then there's the program counter and the instruction register, which hold the address of the next instruction, and they hold the actual contents of the current instruction. So let's go back to our home page, and there's a link there to download Marie. Click on that. If you want to run this on your personal computer, it requires that Java be installed on your computer. So if you were able to run Logisim, which also requires Java, then you should be able to run this on your computer as well. So this is provided by the author of our textbook. It's downloading kind of slowly. Did you guys get it downloaded, or is it going real slow for you guys too? Mine's stuck on 410K. What's that, Brooke? It's not? You know, the last couple of days, I've had problems getting files to download from my website. Have you guys had problems? Maybe it's...
Well, I tried to get to your website this morning and it was down for like an hour. I refreshed it.
Well, I think it's time. Okay, it's time for me to call GoDaddy, find out what's wrong. They're the ones that host my pages. Okay. Okay, let's try this. I just did a search for Marie Simulator in Google, and there's a link here to Student Resources, Essentials of Computer Organization. Let's click on that. And it says click to download the Marie Simulator. And that one looks like it downloaded right away. Cancel this one. So you need to extract them all when it downloads. I would probably put it on my desktop, I think. I mean, that way it's handy, but on the other hand, then it's only on this computer that it's handy. But if you just use it in class or do it on your own computer, it shouldn't make much difference. Okay. Now, there should be a program here labeled Marie Sim. See a program called Marie Sim? That's the one we want. Double click on Marie Sim. And so this is what the Marie Simulator looks like. This window over here is where we load our instructions. This is our registers. It shows us what's in each register all the time. Some of them are 16-bit registers, so we got a 4-digit hex number, but the memory address register is only 12 bits, so it's a 3-digit hex address. And the program counter refers to a memory cell, and memory cells are only 12 bits, so that is only 12 bits wide as well, or 3 hex digits. Down here is our memory. You can actually see what your program and your data look like in memory down here, and there's not a lot of it. It goes up to FF0 or FFF. So this is FF0. This one over here is FFF, which is 12 ones. So it's location 4095. Okay. If your program executes an output instruction, the output will be displayed over here. There is an editor. If you go to File and choose Edit, it opens up an editor for you, which is not much different from Notepad. It just lets you type in a simple program. Then you have to have that program translated for you. And after it's been translated, then you can run the program. Okay. We're not going to do anything with Marie today. I just wanted you to download it and take a look at it. We will be using that probably starting tomorrow. Okay. Now let's go back to our notes. Where are my notes here? There we go. And that's the end of my notes. Okay. So we can close that. And now I want to share my my web browser window. And I want to go back to our home page. And let's take a look. We've got two digital logic labs. You have to create some circuits. So this is an 8-bit adder. Let's download that, and hopefully that downloads. Okay. So actually, I think I built a 4-bit adder for you yesterday. So what we're going to do is we're going to have 8 adders, and we're going to use these components. We don't have to create our own adder every time. We're going to have 8 of these stacked on top of one another. We'll have an 8-bit input called A. We'll have an 8-bit input called B. And whenever we put numbers in A and B, it should output the sum of those two numbers. And we want to take the sum here. We'll have 8 of these stacked on top of one another. We'll have 8 sums coming out. We need to run the top 4 through a splitter and run them into an LED display, a hex display, and then take the bottom 4, run those through a splitter. So we got 4 bits coming in to the second display. Our answer is going to be 8 bits, and you can only do 4 bits in a hex number. So we need 2 of those side by side to display the sum of the 2 numbers. Okay? So that's one part. And the other part is an 8-bit counter. And we also did an 8-bit counter in class today. So I think the instructions for this one are pretty short. Yeah. So design an 8-bit counter using T flip-flops. You can take the 4-bit counter that I gave you, and you can use that as a starting point. And it's an 8-bit counter, so it can go from 8 zeros up to 8 ones. 8 ones is 255. And we want to display the counter. So we need 2 hex displays, one for the high order 4 bits, one for the low order 4 bits. And I want to see those side by side. So every time you zap the clock on it, it should increase the display output by 1. And when it gets to 255 or FF, it should roll over to 0, 0 and start all over again. So that is it for today. Tomorrow we'll start on Marie and looking at how Marie works.